At the very beginning of time there was nothing, no matter, no energy, just absolute emptiness. And then, in a flash so brief it defies comprehension, that nothing transformed into everything. Space exploded into existence. Time began to move. Tiny particles raced outward, forming the seeds of galaxies, planets, and life itself. How could something as vast and complex as the universe come from a state of total absence? How did the deepest silence erupt into a cosmic roar? How did nothing like the spark that became the Big Bang? Before we begin tonight's video, let us know where in the world you're watching from and what time it is for you right now. Post it in the comments below and settle in for a fascinating journey to the beginning of the universe. The idea of nothing may sound simple, but in reality it's one of the most puzzling and mind-bending topics in all of human thought. For thousands of years, from the time of ancient philosophers to the age of modern science, people have been trying to understand what nothing really means. And as strange as it may sound, the word nothing doesn't have just one single clear meaning. Its definition actually changes depending on who's using it, whether it's a philosopher, a scientist, or even a theoretical physicist working on theories about the very birth of the universe. In philosophy, nothing is defined in its most extreme form: absolute non-existence. This isn't just an empty box, it's the complete absence of anything imaginable. No matter, no energy, no space, no time, not even the laws of physics. It is the ultimate void, a concept so pure that many thinkers have argued it's logically impossible to even contemplate. This is a profoundly difficult idea to grasp because we have no experience of such a thing. Every void we encounter is, in reality, teeming with substance. Even the empty air in a room is a dense soup of molecules. The vast expanse between stars is filled with stray atoms, cosmic dust, light, and invisible gravitational fields. This resistance to the void has deep historical roots. The ancient Greek philosopher Aristotle famously declared that nature abhors a vacuum. Writing over 2,300 years ago, he argued a true void was a physical impossibility. His reasoning was tied to motion. He believed objects needed a medium to move through. Therefore, all space had to be filled. For nearly 2 millennia, Aristotle's view held sway. But around 1643, Italian scientist Evangelista Torricelli made a discovery that challenged it. In a simple but ingenious experiment, he showed that when a glass tube filled with mercury is inverted into a dish of mercury, the column falls slightly, leaving a space at the top. This Torricellian vacuum contained no air. This simple device, the first barometer, was revolutionary. It inspired further experiments by brilliant minds like Blaise Pascal and Robert Boyle. Their collective work dismantled Aristotle's long-held belief, proving a vacuum was not just a concept, but a physical reality that could be created and studied in a lab. But even with proof of a vacuum, scientists still clung to the idea of an invisible, luminiferous ether, a necessary medium for light waves. This theory fell apart in the early 20th century. Albert Einstein's theory of relativity showed that light doesn't need any medium to propagate, traveling perfectly through the vacuum of space. Just as science seemed to settle on a truly empty vacuum, the revolution of quantum mechanics turned everything on its head again. In the early 20th century, scientists discovered that what we once thought of as empty space wasn't empty at all, but a dynamic and energetic place. This bizarre reality is a direct consequence of the Heisenberg uncertainty principle. This tenet of quantum physics states that you cannot simultaneously know certain pairs of properties like a particle's position and momentum with perfect accuracy. A similar uncertainty exists between energy and time. For a space to be truly empty, its energy would have to be exactly zero, which would violate this fundamental rule. This means that even in a perfect vacuum, there's a constant flicker of borrowed energy. This energy allows for tiny temporary virtual particles to spontaneously pop into existence, often in matter-antimatter pairs, before almost instantly annihilating each other. This seething, effervescent sea of transient activity is what physicists call the quantum foam. In 1948, Hendrik Casimir predicted something strange. Place 2 uncharged metal plates close together in a vacuum, and they will move toward each other. This proves the vacuum is not empty. It's filled with quantum fluctuations, and the tiny gap restricts these fluctuations, creating a pressure imbalance that pushes the plates together. In quantum field theory, every particle isn't a ball, but a ripple in a field filling all of space. The electromagnetic field gives rise to photons when excited. Likewise, electrons and quarks are simply localized vibrations in their own unique fields, giving substance to the seemingly empty cosmos. One of the most famous is the Higgs field, which gives particles their mass. Even at rest, it has a non-zero value. This baseline energy permeates space, and interaction with this field, a kind of cosmic drag, gives particles their substance. Mass exists only because the vacuum isn't truly empty. The standard model of cosmology says the universe began from an incredibly hot, dense point, a singularity. At that moment, all matter, energy, space, and time itself came into existence. The entire cosmos was compressed into a point of unimaginable density, where our current laws of physics completely break down. This means there was no before in the usual sense because time didn't exist yet. If time started at the Big Bang, asking what happened before is like asking what's north of the North Pole. The question is meaningless. The universe may form a closed surface in time, without a starting edge or moment of creation. In cyclic models, for instance, the universe goes through endless cycles of expansion and collapse. A previous universe might have collapsed in a big crunch only to rebound in a big bounce that became our Big Bang. In this view, the nothing before our universe was simply the compressed remains of a previous one. According to the theory of inflation, the universe didn't start out expanding slowly. It began with a burst of unbelievably fast expansion in its earliest moments. This stretched the universe from subatomic to astronomical size almost instantly, smoothing its initial conditions and solving key puzzles within the standard Big Bang model. Instead, the Big Bang could have resulted from a tiny quantum fluctuation, a random energy ripple in what scientists call a false vacuum. This is a highly energetic, unstable state of nothingness. A spontaneous decay from this false vacuum to a lower energy state could have released the colossal energy that powered the Big Bang. In such a grander picture, our universe could be just one bubble floating in a vast cosmic sea, constantly spawning new universes. This is eternal inflation. In this cosmic foam, countless other universes may be forming, each with its own unique physical laws existing forever beyond our reach, born from the endless energy of nothing. One of the earliest and most influential thinkers was Georges Lemaitre, a Belgian priest and physicist, who in the 1920s suggested the universe started from what he called a primeval atom. This radical idea proposed a definite beginning, challenging the prevailing view of a static cosmos and laying the essential groundwork for modern cosmology. A major leap forward came in the late 1920s when American astronomer Edwin Hubble made a surprising discovery. He found that distant galaxies were moving away from Earth, and that the farther away a galaxy is, the faster it recedes. The first concrete evidence for an expanding universe. The light from these galaxies was stretched toward the red end of the spectrum, a phenomenon called redshift. Similar to a siren's Doppler shift, this is caused by the very fabric of space expanding, stretching light waves as they journey across the cosmos. In 1964, scientists Arno Penzias and Robert Wilson were using a large horn-shaped antenna when they picked up a strange, persistent hiss from all directions. After ruling out every earthly source, they realized they had accidentally detected the faint, ancient afterglow of the Big Bang. This faint glow is the leftover radiation from the early universe, the cosmic microwave background. According to the Big Bang theory, the universe was once a hot, dense fog of particles and radiation, a plasma so opaque that light could not travel freely. It is like a frozen snapshot of the universe when it was just 380,000 years old. At this point, the universe cooled enough for atoms to form, making it transparent. Its smooth temperature pattern with tiny variations matches exactly what the Big Bang theory predicts, acting as the seeds for all future structure. Scientists believe everything began at the Planck epoch, just 10 to the minus 43 seconds after time started, a point where our physics breaks down. Immediately after, a process called inflation suggests the universe expanded by a factor of at least 10 to the power of 26 in a fraction of a second. That's a number so large it's hard to even imagine, but it neatly explains the universe's vast scale and uniformity. Gravity then amplified the tiny density variations from the early universe. Some of these clouds eventually collapsed under their own gravity, igniting the first stars and quasars, brilliant beacons that lit up the cosmos. Over time, this structure formed the vast cosmic web, a gigantic pattern of filaments and voids where galaxies are arranged in long strands separated by enormous empty spaces. Astronomers studying distant exploding stars called supernovae in the late 1990s made a shocking discovery. The universe's expansion wasn't slowing down as expected. it was actually speeding up. This discovery pointed to a mysterious repulsive force, now called dark energy, that pushes the cosmos apart. The Big Bang Theory is a monumental achievement, yet it leaves us at a profound boundary. It explains the universe's evolution, but not its ultimate origin. Understanding what came before the Big Bang may depend on how we define that ever-elusive concept: nothing.